Hey everyone, thanks again for joining us here for today's webinar, End Cold Starts with Your Serverless Applications with AWS Lambda Provisioned Concurrency. Again, my name is Chris Munz, currently a Senior Manager, Principal Developer Advocate for Serverless at AWS. I've been with AWS now for a little over 7.5 years across a number of different roles, but for the last 3 years have been talking about serverless. And so I kind of do things like this. I travel to conferences, I create blog posts. If you read the Compute blog, you might have seen some of the things that I've written, as well as the things that my team writes. And so we are 100% focused on the topic of serverless and excited about helping you to grow and understand what serverless means for you. So what are we here for today? Well, we've had a number of exciting announcements in the last couple months here for the world of serverless at AWS. Just at the beginning of December in 2019, we had AWS reInvent. And reInvent is our yearly user conference that we have where developers and builders and architects and folks from all over the world come together and share knowledge, get to learn more about AWS's products and how they work and best practices. And we also sometimes have some pretty cool announcements along the way. And so we're going to talk about one of those here today, which is called Provisioned Concurrency. And really the gist of what you want to walk away with here today is that now more than ever, performant interactive applications are made easier with Provisioned Concurrency. And again, we'll be talking in depth about that here today. Now this is a kind of, you can think of it as a 400 level talk. So we're not going to be going too much into the lower aspects of Lambda, but if you're an experienced Lambda developer, or at least you have some understanding about what Lambda is, this is definitely the webinar or the tech talk for you. Kind of flow for today. Again, first, we're going to talk a little bit about cold starts and concurrency. It helps to really kind of understand a bit more about what it is that Provisioned Concurrency helps makes better and how it works. And then we'll kind of wrap up with talking about some general best practices for all. Okay, so let's dive into cold starts and you. And again, I picked this warmer picture here to kind of emphasize the fact that cold starts, I think there's a lot of fear, uncertainty, and doubt in the technology world. You might read a lot of blog posts that don't talk about it really necessarily in the right way. And so there's a lot of stuff out there that isn't really accurate. So I want to kind of dispel some of the rumors and get really to the heart of the matter of what a cold start is. Now, a cold start is an event that happens when a system needs to create some sort of new response in event to, say, a request or an event coming in from a system. Cold starts are not unique to Lambda. You see cold starts in container orchestration. You see cold starts in high-performance computing, workload management, and a number of places where resources, say IT resources, need to be spun up. Now for Lambda, what happens, what we consider a cold start, is when a new execution environment, that is the underlying infrastructure that executes your code, needs to be spun up in response to handle requests that have come in. Now, after they've been spun up, we'll talk a little bit more about this later, they enter a warm state, which allows them to then handle subsequent requests. What this means is that typically for most customers, you end up seeing a very, very, very small percent of your invokes actually end up being cold starts. And this is for production workloads, if you will. So it's the kind of thing that you see very often if you're doing development work. Say you create a function, edit a function, and then execute it, you'll see a cold start for that. But again, if you have a workload that's seeing any sort of consistency in the amount of traffic that it gets over a period of time, even workloads that ebb and flow throughout the day, you typically will end up seeing a very, very small percentage of those workloads end up being in a cold start. We'll talk about why here. Now, one of the things about cold starts is that they can also vary really greatly in terms of how impactful they are to your application. And in fact, we see cold starts that will be anywhere from under 100 milliseconds to even over a second. And again, we'll break down exactly what might be happening there. And so why is there this variance? Why can you see this huge gap between those? And also, why do you see it for just some small percent of your executions? So let's talk a little bit about a function lifecycle. So the first thing that happens typically for Lambda is that a request is made to Lambda's API. Real quick side story here. It's important to note that the only way that you invoke a Lambda function is via its API. There is no port, there's no socket, there's no otherwise way that you can invoke or interface with the Lambda infrastructure that's running your function. And so whether you are executing via an API gateway or an S3 bucket or Kinesis or any of the number of other services that can invoke Lambda, they are all executing that using the AWS SDK behind the scenes. Now this is important, and we talk about how this changes later with how environments are provisioned with provisioned concurrency. Another important thing to know about Lambda, as again, as a quick aside here, is that there are technically 3 different execution models. There's synchronous. Again, in the example of an Amazon API gateway, I make a request to my gateway to a specific API call that I want to make. It's then going to execute a Lambda function on my behalf, which is then going to return a response up to API gateway. That's a synchronous request. For an asynchronous event, you could think of, for example, I put an object into an Amazon S3 bucket, or I put a message into an Amazon SNS topic. That then goes and invokes Lambda on my behalf. Now, technically, for asynchronous events, it actually ends up putting that message into a queue. And then the Lambda service takes that message out and executes it on your behalf. But again, in this situation, there's no path back out to the originating thing or application or service that put a message into that topic or an object into that bucket. And then finally, we have a stream or pull-based model. This exists for Amazon Kinesis data streams, for Amazon DynamoDB streams, and for Amazon Simple Queue Service or SQS, where we run a puller on your behalf from those resources, pull messages or events out of them, and then execute your Lambda function with those. And again, this will be important as we talk more about concurrency and how provisioned concurrency is impactful or not, depending on the execution model that you have. So let's go back again to the situation where I have a new event that's come in. So I have a new event that's come in to Lambda's API, and Lambda's API then needs to turn to a component of it that has to say, do I have any execution environments that are available for this application? And in this case, it's going to look at basically a state that it stores about this. And if it does, which is really what we want to see, then it will go and directly pass in the event to the underlying compute resource that is available in Warm for it. That will then invoke the handler of your code, which will then ideally go and complete the invocation for you. And again, this is the situation that you see overwhelmingly for a in-production Lambda-based application. Because again, we keep resources around Warm for you, which means that as subsequent requests come in, they should land on a Warm environment. And so overwhelmingly, this is what a majority of your requests will, or events I should say, will end up going through for most workloads. But let's take a situation where there isn't an available workload or an available execution environment. So if there is no execution environment that's available, so let's say this is a brand new function, or you've just updated your function or made a change to its configuration, then the next thing that the service has to do is find an available compute resource. And so on the Lambda side of things, we run those servers that are in serverless that you don't have to deal with. And we run massive pools of capacity globally across the various AWS regions that we have. And so we find one of those resources. We then take your application artifact and download it to that compute resource. We then have to start up the execution environment. So depending on the configuration that you have for it, for things like memory, we will then go and basically fire up the execution environment that it's running with your code in it. We then have to execute the init code or pre-handler code that your function has, which after that point, we will then have the event passed into the invoke handler, or to your code handler, I should say. And then again, ideally, you would have a complete invocation of your function. You would execute your code based on the event and then be finished. And then again, subsequent invokes of that environment would follow the warm start. We don't need to now find that resource again. We don't have to download your code again. We don't have to bootstrap the environment, and we don't have to execute the init code. So again, for most of your requests, you would end up seeing this type of warm start environment. So there are some other things, though, that are important to know in terms of warm and cold start factors and basically things that happen behind the scenes. So one thing that you should know is that we actually don't just keep these environments around for forever. Basically what happens is that these environments can idle out. And so based on the activity of your application, if it's not being used, then we will actually take those resources and recycle them back into another availability pool over time. Also, if the resources are actively being used, we still, however, will flush roughly every couple of hours those resources out and then pre-create new resources for you. And this allows us to make sure that execution environments are always kept fresh and that we could apply any sort of updates to the underlying resources that we might need to. Another thing that could happen is that the underlying infrastructure could have a failure. We could have a failure of a physical host up through an availability zone. And in situations like that, then what would happen is you would see a new cold start because we potentially might be short the resources that you need as an invoke is coming in. And then lastly, on occasion, we will actually bypass a warm and execution environment in order to help rebalance your workload across the availability zones. And this is basically to help make sure that we don't have a blast radius issue if we did have a significant outage where we would lose all of your warm functions. Again, most of this stuff is completely transparent to you. You don't end up seeing it or experiencing it. And by and large, your application is not affected because of that. Now, another aspect to how Lambda works is that there is no affinity for the repetitive requests, or I should say to the subsequent requests that you get to a piece of warmed execution environments. Essentially, there's no concept of sticky sessions. There's no ability to target warmed environments. And so you want to be really cautious about anything that you might be doing, such as storing state inside of a Lambda function, either in, say, the temp storage space or in the memory. Again, because of the factors mentioned above, because of some of the concurrency aspects that we'll talk about here in a bit, you don't really have a way to target that. So this is, again, not necessarily a direct factor towards performance, but just a general best practice that you want to think about. And then finally, anytime that you update your application code or change your configuration function, we will have to basically then go and cause all of the warm environments considered invalid, and they'll behind the scenes get flushed out after they finish whatever execution they have, if they have any executions, and then all new executions of your code will go to new environments via the cold start. So again, this is something that happens anytime that you take an action, and this is to make sure that we're not executing your code on, say, either the wrong code or on the old environment type. As soon as your function has been updated and is in an updated state, then all of those new executions will go to the new environments. Now, when we talked about the life cycle of things that happen in terms of a cold start, there's basically a couple of things that happen on the individual we consider to be worker host. Again, this is the underlying compute resource where the code actually gets executed. So after we've identified it, and then we go and download your code and start the execution environment, again, then we have to execute your init code, and then we execute your handler. And what you can see here is just basically a dividing line between the things that we can impact on the AWS Lambda side of things, and then the things that you can impact based on best practices with your code. So let's talk a little bit more about some of the things that you can optimize for in your application. So an example of an application here, I have a really basic function handler. Again, this isn't any specific language. This is just kind of some pseudocode. So I have my handler here. And then typically what I'm going to have in, at least in most serverless Lambda applications that we see, is I'm probably going to need to import some other packages. Again, depending on my language, these can be imported in a number of different ways. I might also need to execute some pre-handler code. So maybe I want to pull some secrets out of something like AWS Systems Manager Parameter Store, or out of AWS Secrets Manager, or out of, say, a product such as Vault or some sort of other secrets type of management tool. Or maybe I then need to connect to a database. So maybe I have a relational database that I'd like to connect to, or a non-relational database, or maybe I need to pull down training data from a machine learning workload. There's a lot of things that we could end up wanting to do before a handler in order to optimize our handler later on. So again, dependencies, configuration information, executing common helper functions. We then might also have then these helper functions defined inside of our function code. And one thing that we don't talk about here in this talk today is that you could use something like Lambda layers to help manage these resources for you in terms of being able to allow for easy code reuse and artifact management. But again, you'll typically have then these common helper functions in here. Now, it's important to note that basically everything that you're doing here outside of the handler is getting executed on that initial init and cold start. So right here where we have this full cold start, all of the stuff that happens outside of the handler here ends up getting executed. Now this is important because it essentially is a blocking action before your handler can process the event that's being passed into it. So when it comes to thinking about pre-handler code dependencies, any sort of, say, global variables that you want to initialize, really less is more. The less that you do and the more focused and targeted you are at the resources that you do include, the better overall performance your function will have during these cold start times. Again, you want to import only what you need. As much as you can streamline or trim down, say, any sort of third-party SDKs or other packages that you might include with your code, you definitely want to. If there are certain packages that you use only during development time but not during, say, production, then this is, again, another situation where you want to think about how you can make sure that your production application doesn't include those other things. Again, pre-handler code could be really useful for doing things like connecting to databases or getting secrets or API keys or pulling down machine learning data. But again, it's code that will block the execution later on. And so you want to make sure that when you're doing these, that it's definitely going to be something that could be used in almost every single invocation that you might have. If you have certain code that you would execute only during, say, a certain failure situation or during, say, a less likely processing of an event, then you might want to actually wait until you have that situation inside of your handler before you import or execute that code. A couple of other things to remember here, you can lazily load variables inside of the global scope. Again, if you don't need it, don't load it, don't instantiate it, don't pull down the data. And then one last thing that you want to make sure about here is that for the languages that do allow you to establish, say, global variables or any variable outside of the handler, you want to make sure that you're paying attention to where the state of that variable gets stored and how it might exist between executions on the same execution environment. And when we put all this together, we look at the data from our customers and the applications that they're building, what we find is that overwhelmingly, the init code, that pre-handler code that you write that includes, again, your libraries, that talks to databases, data stores, that maybe talks to different other services to get secrets or API keys or what have you, this is one of the largest pain points for cold starts. And so again, insofar as you can follow the best practices previously mentioned, that will help a lot. But we'll talk here a bit, again, about how provisioned concurrency helps you with this even further. Okay, so how can you measure the performance impact of these? Again, because this is code that you're executing, because you might be making calls or doing other things, I do find that it is really important to measure this. The easiest way you can do this is using AWS X-Ray. So X-Ray is a profiling and troubleshooting service that is deeply integrated today with Lambda and API Gateway and a number of other AWS services. It has an optional SDK that you can use, and I would say that if you want to measure your init code, using the SDK is really important, because one thing you can do with the SDK is create what are called custom segments. Now, those custom segments allow you to capture specific pieces of information about the code that's being executed inside of your function. And so while you could generate things like this system map that you see here, one thing that custom annotations allow you to do is when you go to the waterfall view of the flow of your application, you'll actually be able to basically create annotations for where you spend your time in your pre-handler code. And so this can be a really valuable way for you to debug even further what is happening inside of your init code, and then potentially be able to tune it or change it over time. The next thing I want to talk about is function concurrency. And again, this is a separate topic here, but very much important in the realm of provisioned concurrency. Now, a single Lambda execution environment can only process a single event at a time. Essentially, once you kick off that workflow that you saw before, more or less that is a single, effectively threaded motion throughout the ecosystem of function execution. So regardless of the event type, whether it is synchronous or asynchronous or pull-based, that is only a single event. This includes in the pull-based models where you have cases data streams, SQS, and DynamoDB streams where it can process a batch of messages from those still count as a single event. So what this means is that as you have, say, concurrent new events that come in, that will cause a new execution environment to need to be created. And again, this is all managed for you by Lambda, so there's nothing that you have to think about. But you do have to pay attention to a couple of things. One is that for Lambda, there is a per region limit on the amount of concurrency that you can have. The second is that aside from that, there is also what is called the burst rate. The burst rate impacts the amount of scaling that you can do at any point in time. And so as you see here from the table, it's anywhere between 500 and 3,000 depending on the region. And again, this impacts a point in time for scaling of your function. So dive a little deeper into this. So let's assume that I get a request, and this is for a function that does not have any execution environments available to it. So maybe it is a new or an updated function. What's going to happen then is it's going to cause a cold start to occur. That cold start will finish. I'll get through my init process, and then my code will execute. During this time, this execution environment between the cold start and the execution is completely blocked from being able to handle any other requests. That compute resource is completely consumed as part of this. Now let's assume that I get 2 more executions that come in at the same time. As we can see here, those requests would each also have their own cold start and then begin their own executions. And this would continue on as more requests came in. So let's just say before these 3 finished, I got 2 more requests. And so as we see here, because those came in, those invocations came in while my other environments were still executing, what happened here is that it caused other requests in other execution environments to be spun up. And so we see for requests 4 and 5, those new execution environments. But what's interesting here is that there is a point in time where the execution ends from the first request. And then after that point in time, that environment is now free and warm and available for new requests. So if I get request 6, the system is going to target it towards that initial environment that is warmed and available, and so on. So you can see here I get a bunch of other requests. As those other execution environments are freed up, they become available. Now you see a point in time down here for request number 9, where at that point all of the current execution environments are currently processing a request, and so that again causes a new cold start and a new execution. In terms of concurrency, we measure concurrency at a given point in time. So if we look at how concurrency is measured throughout the application that we're showing here, you can see a couple of points. So we see, for example, early on where I reach 3 concurrency, when request 3 causes its cold start of its execution environment. We see then that goes up to 5 when I get to the next request 4, request 5. However, that drops back down to 4 during the time after request 1 finishes execution. It also then is at 4 after request number 3 ends and number 7 starts. But then we see actually when request 9 comes in that we at that point in time have 6 concurrency. And so again, you can get kind of the idea here for how these environments are reused. Now, if we could expand this over a longer period of time, again, what we would see is that we would have less and less of these cold starts, and we would see more and more executions happening that don't require those cold starts because they're landing on warmed resources. Now, again, this is one of the key aspects of how Lambda handles scaling for you. And so again, this isn't something that you have to think about. This is just the way that the platform handles this scaling. Now, we can assume, though, that if we got all at once a larger burst of requests, that would cause many, many, many more cold starts. Similarly, after those requests, after those environments had been spun up, the subsequent requests to them would hit those warmed environments ahead of time. Now, one thing I wanted to touch on real quickly here with concurrency is that if we think about the model that we have here, where we're creating more and more and more execution environments, we could be consuming a number of resources downstream. So for example, potentially we are connecting to databases, or we are talking to another service's API and getting, say, secrets or API keys or something similar like that. What you have is the potential that Lambda functions could end up essentially starving downstream resources. And again, this could be database connections or something like another API or service that you're talking to. Concurrency is a shared pool by default inside of an AWS account. So what this also means is that across all of the functions that you have configured, so for all of the functions that look like this, regardless of what function it might be, they're going to be taking out of this total concurrency that you have in your account, which today is 1,000 concurrency per account per region. And so when you put all this together, what it means, again, is that Lambda has the ability to potentially cause resource starvation depending on application configuration and workload. So a capability that we have to help you control that is something called Provisioned Concurrency controls. Much like the name sounds, this could basically act as a ability for you to limit the amount of concurrency that can happen inside of a function. It also acts as a reservation across the total concurrency pool that you have in a given region and account. And so you could say, for example, that for a given function, I want to ensure that it can always execute up to 50 concurrency. And so we both reserve that from the total account concurrency, and then we also basically put a limiter effectively on top of that. So if we had it set to 50 and the 51st request comes in during that same time, that request would see a throttle. Similarly, if we had, again, an account that had 1,000 concurrency in it, and we reserved 50 of them for a given function, that then leaves only 950 concurrency for the other functions in the account. Another cool aspect of this is you can actually use it as effectively a kill switch or an on-off switch for a function. So let's assume that you did have some sort of downstream resource impact, something got deployed that went wrong. You can use concurrency controls to flag a function off versus, say, having to push code out to disable it or to disable the event source or do something like that. And so in times of, again, something's gone boom, this could be a great way to control and recover from that. Okay, so we've talked a little bit here about cold starts. We've talked a little bit about concurrency and how concurrency matters. Let's kind of put them all together here and talk about provisioned concurrency. So again, just a couple weeks ago at AWS reInvent, we announced Lambda Provisioned Concurrency. We're really excited about this feature. This is based on getting feedback from customers pretty much from the beginning of when we first launched Lambda. And, given what we've talked about here so far, what's important to understand about it is that basically what it does is pre-creates the execution environments and executes the initial bootstrapping of them all the way up through the init phase. Now, this might sound like a great thing for all Lambda workloads. However, we really are encouraging customers to think about it just for interactive workloads. So those that are really latency sensitive, that you do have a concern about the overall performance of their execution time. This does not change how your functions actually run. It doesn't run it on any sort of other special compute resource. It doesn't do anything to optimize your code. It just basically takes care of provisioning the resources ahead of time. We'll talk about that here more in a moment. One other great thing about this is that it greatly improves the consistency. At the end of the day, the way that Lambda works is when we execute functions and we go through that full workflow that we saw before, is you have a number of services that are calling other services to find a resource, to download your code, to bootstrap that code, to execute your init code. And what you can have across those is quite a lot of variance in the latency of how long it takes to execute those things. And so what it could mean is at the tail end of the performance curve for Lambda functions, you actually saw quite a bit of variance in the consistency in terms of how long it might take those cold starts to happen. Provisioned concurrency definitely addresses that and removes it. You can see kind of here in the chart to the right how much more consistent the orange boxes are versus the blue ones. And again, there's always going to be some variance based on the overhead or what might be happening inside of the Lambda we consider substrate, essentially the management services. But again, much, much, much greater improved from how it was previously. You really don't have to change your code for using this. So provisioned concurrency doesn't really require you to do a lot in terms of how you think about the way your functions are written, how you process events, how you handle events. It will, however, change a very small bit how you think about init code. And I'll talk about that here more in a moment. It's integrated with AutoScaling. I'll show an example of what that looks like here. And then I think one of the coolest parts about this service is it does involve a different price model. However, if you use provisioned concurrency and utilize it really well, so in this case, you're using it for the right reasons, it supports your workload, you're not just, say, setting it to a high number and leaving it for forever, then you can actually end up saving money with this. And so we didn't want this to be the kind of a thing where customers who were using it, who needed it, automatically had to pay more for it. And so again, what you find is if you have a higher utilization, typically the numbers I've been seeing are, say, about 70% or higher, then provisioned concurrency is actually going to be cheaper than what we now consider on-demand Lambda. So before we talked about what the lifecycle looked like for a full cold start, again, you made a request to Lambda's API. It would then go and see if there was a warm execution environment. If there wasn't, it had to find a compute resource, download the code, start the execution environment, execute your init code, at which point then it could take the event and invoke the handler, and then again, it would complete that invocation. With provisioned concurrency, this changes. Instead of it being based on an API call, a Lambda API request coming in, instead what happens is when you configure your function, what we do after that function configuration has been recorded is we then find the available compute resource or resources. We download your code, we start up the execution environment, and we execute init. Again, this is happening outside of the request path. So this is going to happen as soon as you save the configuration for your function that is configured for provisioned concurrency. After that point, then you resume the normal warm start function lifecycle, where again, as invocations come in, the Lambda API goes to find a resource. In this case, it will find one for provisioned concurrency up through the amount that you configured. We'll talk about that here in a moment. It will then go and invoke your handler and again, complete the invocation. And again, this will happen up through the number of concurrency that you have configured for this function. If we put it all together here, there's actually this chart here from our documentation which spells it out a little bit better. Assuming that we have what you see here with the gray line, which is the kind of in-flight requests. If you look at the orange line, those are essentially the number of execution environments, or in this case it says function instances that have been created. And then what we've done is we've set here at a certain value provision concurrency. And so for all of the requests that come in underneath that provision concurrency, then they're going to, again, go right through the warm start pattern. They will not see any of the cold start or init latency. However, above that provision concurrency line, you do end up going through the normal on-demand Lambda behavior for seeing a cold start and seeing inits. Again, up through the amount of traffic that, or up to the request traffic, I should say, that is different over time. Some other things about this. So provision concurrency will basically drop the overhead on your function starting from the service side and the cold start side to less than 100 milliseconds. So it is going to change that to an overhead of double-digit request latency, which again is a great improvement over what it was in the past. Another thing about this is that you have to configure this to use or to be targeted against Lambda functions that have versions or aliases. Now, versions and aliases are a best practice for Lambda. We encourage all customers to use them. It allows you to really follow good developmental practices. But a part of the reason for this is that when we configure provisioning concurrency, we then have to go and actually provision those resources for you. And in an environment where you could have, say, a lot of function updates, or you could be doing a lot of development work, this could end up being really, really thrashy for the resources behind the scenes. And so what this allows you to do is to do normal development practices, and then when you're ready to go to production, you can then update, again, either for a version or an alias. My recommendation actually would be for an alias. You could have an alias that says something like prod, and then it will spin up the provisioned execution environments for that configured amount. Now, when you do go and launch provision concurrency, it follows the same burst model, essentially, that normal on-demand Lambda does. So it provisions concurrency up through a certain amount per minute. So we see here that it is that the soft limit is at 500 provisioned per minute. And so if you configure this, for example, for 5,000, then it could take up to 10 minutes to go and provision all of those resources. This is just a soft limit, but it is something that you want to be mindful of if you are looking to do, say, rapid development against this and need to spin up a ton of provision concurrency. You might want to reach out to support and get that limit changed. Again, there's really no changes to function handler code. So the stuff that you do inside of your function will stay and execute exactly the same. You shouldn't expect that to execute any faster. And so that's where you want to continue to follow best practices in your application code. We'll talk about some of this here at the end of this talk. And you are still limited, finally, by the overall account concurrency for your given region. So again, by default, that's 1,000. That means you can only set up to 1,000 provisioning concurrency today. If you go and you change that limit, then obviously that can increase. Now, there are a couple of things that you should know about provisioning concurrency that aren't readily obvious when you initially find out about it. One thing that we do is that in order to maintain availability and to help with the scaling of your functions over time, we actually create more resources behind the scenes than you request. So if you requested 100, we might provision 150 or 200, let's say. Now again, you have no visibility really into that, with the exception of the fact that because we perform the init of your code, if you say have any logging statements or make any calls out to other services during that init, you will see the artifact of that. And so you could see extra log files, you could see log lines that show that things have happened, but that don't then show an actual execution of the function handler code. And again, that is just because it allows us to help make the availability of your function higher and to scale it more quickly over time. The second thing that you will see is that we still end up basically reaping these environments from time to time. Now, this is not the same as with on-demand, how when a function goes idle, after time, we will basically remove that execution environment. In this case, because you are expecting there to be this provision concurrency for you, over a longer span of time, what we will basically do is create more execution environments and then tear down old ones that aren't being used. Now again, this doesn't impact your code changing or any configuration change. This is strictly just for the ability for us to keep the underlying infrastructure fresh and updated for your application. And then finally, one last thing, and we didn't talk about this in the earlier part of the webinar, is that when you first launch a Lambda function in on-demand mode, we actually burst the CPU slightly to help make that init process be even less painful. And so we give you a little bit extra CPU than would normally come for your configured memory. We'll talk about that a little bit more here towards the end of the talk. But we don't do this now in provision concurrency. And so you can see if you are doing profiling and troubleshooting of your functions is that with provision concurrency, that CPU burst doesn't exist. And so your init time will take what it would normally take if you didn't have that burst. So in this case, it will show potentially that it could take a little longer. Now, this will depend on what you're doing during your init code, your pre-handler code. And so you may notice this, may not notice it, but at least now you know why you might end up seeing that. I mentioned earlier that pricing for provision concurrency is a little different. And so there's basically two ways that provision concurrency has changed compared to on-demand Lambda pricing. And again, you can read all about this at the aws.amazon.com/lambda/pricing website. The first is that the way that provision concurrency is calculated is based on the number of provision concurrent functions that you have configured over a period of time rounded up to the nearest 5 minutes. So because it takes time to create these provisioned concurrency resources, because you typically are going to want them around for a period of time, we basically look at it in 5-minute intervals. So that's an important thing to note. The second is how duration is calculated. So duration is still calculated the same, basically that it's based on the execution of your function rounded up to the nearest 100 milliseconds. What is different here is that it is a lower price compared to on-demand Lambda. And again, as I mentioned before, what this means is that if you're heavily utilizing provision concurrency Lambda functions, you could actually end up saving money. Now, the cost for requests doesn't change in this model. It's still 20 cents per 1,000,000 requests. Now, one other thing about this that, again, may not seem super obvious, when we talk about the duration that's calculated, that actually also includes function init time. So when you do pre-provision these functions, even if they're not getting an event invocation, because they are still executing the initial bootstrapping of the environment and setting up and then your init pre-handler code, you do actually pay for that amount of compute. And again, it is rounded up to the nearest 100 milliseconds. In terms of configuration, super easy. So via the console, you basically set the version or alias that you want to use. In this case, you see that I have version 1. You see the provision concurrency that I'm setting, which is 5,000. After I click save on this, what happens then is it begins to provision that concurrency behind the scenes. Again, this happens in a rate of 500 per minute. Now, it's not an exact even 500, 500, 500. As it finishes provisioning some of that concurrency, it will continue on there. So you can see, again here, not square numbers with 500 showing up here in the status bar. Another thing I'll talk about here real quick is that you can also configure this outside of the console. So one way you can do this is with AWS SAM, or Serverless Application Model. This is a template-driven system that's built on top of CloudFormation for managing your serverless applications. It's got a bunch of cool capabilities and things that you can do with it. If you're not familiar with SAM, just to kind of help get the point across, this is a template that has approximately 20 lines of code. From those 20 lines of code, I get a Lambda function, an IAM role, an API gateway, and a DynamoDB table. Well, you can also configure provision concurrency with SAM and CloudFormation. So again, this is going to be based on using AutoScaling, which I totally recommend if you're going to be using provision concurrency. And so what we see here is basically I have an AWS application AutoScaling target, scale input target, and then I also have a scaling policy. And now this will be applied to my function and to the alias or version that's listed here. And then basically what this says is I'm going to set a max capacity of 100. I'm going to send a min capacity of 1, so scaling again up from 1 to 100 in my provision concurrency. And then what this is going to do is it's going to set the target value basically for utilization. So for utilization, I'm aiming to get for 70%. And then if it sees that, then it will go and increase the amount of provision concurrency that I have. And this is just a really brief example of this. Again, you can get really finite, tweaked kind of policies for this. But again, you can do this either via the console, via SAM, via CLI, or via CloudFormation. And then after those resources have all been set up, then what you'll see is that the status for this function has been set to ready for provision concurrency, and then you know that all of that concurrency is available. Now, if you have a function that is currently being invoked during this time, as soon as this concurrency is available behind the scenes, so we saw before the screenshot where it was at 3001 of 5000, as that concurrency comes live, it does become available, and so it will show up as warmed infrastructure. It is not at that point in time that the function itself is not available for execution. However, any traffic that goes above the current configured concurrency at that point in time will be just utilizing on-demand Lambda functions. So let's round up here with just some other performance best practices and some other kind of good news tidbits that you might have missed in the last couple of months here. You know, again, because provision concurrency doesn't really change the way that your functions execute, the core, most basic kind of performance knob that we have with Lambda functions is the amount of memory that you've configured them for. And this doesn't change with provision concurrency. So as you increase the amount of memory for a Lambda function, it increases proportionally the amount of CPU and networking capacity available to it. As an example, if I have a function that has 128 megabytes and I increase it to 256, I've effectively doubled the amount of memory. If I go then and increase it up to 512 megabytes, I've then doubled it again. And so as you turn that knob from 128 megabytes all the way up to 3 gigabytes, you'll see that increase. Let's think of it another different way. So again, let's assume that we have a really CPU-intensive application. And this is an example of an application that is kind of overly CPU-intensive, where we're calculating a number of prime numbers, which again is probably not something you're going to be doing too often, but it's really just kind of to highlight here what we're getting towards in terms of how this can improve your performance. So we see here as we go from 128 to 1024 megabytes, that my function duration basically goes from 11.7 seconds all the way down to just shy of 1.5 seconds. So clearly we can see the performance improvement. But what also comes with this is a difference in cost. And now we charge basically two different ways with Lambda. We charge based on the configuration for memory times the duration of your function. So as your function gets faster, it can actually become lower cost. So if we look at the differences here between the best and the worst in these, and they're kind of color-coded slightly differently, what we end up finding is that while 128 is the cheapest in terms of the cost for the function execution, if we compare it against 1024, which is the fastest, we end up shaving off about 10.25 seconds, and it only costs us 0.0001 of a US dollar. So for your application, you have to ask yourself the question of, is it worth it for me to have that performance difference? And again, if you're going to be looking at using provision concurrency, I would really, really encourage you to take a look at turning this memory knob and looking for the increased performance that you get. Another thing you can do is there's an open source tool that is out there which will actually allow you to test this. And so you can look at it. It's from one of the technical evangelists here at AWS. It is for measuring the performance between Lambda functions. Sorry, it's from Alex Casablani. We will paste the link for that here in the chat so that you can go and find that tool. But it's a really great tool for benchmarking and comparing performance at different memory configurations for your function. So again here, as you turn that knob, your functions will potentially become faster depending on how CPU bound they are, and then with that can come lower cost. Going back to how you turn this knob, so one thing that happens is when you reach 1.8 gigabytes, we actually give you a second core. And so then it continues to scale again with the proportional amount of memory that you have configured. But one thing that you might find is that after you cross that 1.8 gigabyte bound is that you don't end up having any more improvement to your function. And this is typically because your function then is just single-threaded and doesn't support multiple cores. Now that is very common, and so generally speaking, most customers do not see a performance improvement above 1.8 gigabytes. The difference will be if your function is in any way, shape, or form I/O bound. So if you are, say, pulling down a lot of data from S3 or over the network in some way, or you're making, say, a ton of HTTP calls, those are really the only places where you will see performance improvements above 1.8 gigabytes, unless your code supports multi-threading or some sort of fork processes inside of it. Again, typically we don't end up seeing that. Another thing we want to touch upon, which we're not spending a lot of time talking about here in today's talk, is the impact that VPC has on Lambda functions. And the good news is the impact is almost nothing now. So a couple of months ago, back in September, we first announced that we were rolling out improvements to how VPC networking works with Lambda. What you can see from the two screenshots here is kind of this before and after effect. What has changed is that we have moved from a model of using multiple elastic network interfaces inside of a VPC to something that we now call a VPC to VPC NAT. You can read all about it in the Compute blog post that you see the title for above. We'll also paste the link for that here in the chat. Best news that I could share is that as of reInvent, this is now basically available in all public regions. And in that blog post, we also document where it is available in non-public regions. But currently, if you're using a public AWS available region, then this is now there by default. And so there's nothing you have to do to flag this on or configure this. It is completely rolled out, and you will just be seeing it happen behind the scenes. Awesome. So we've covered a lot of different things here today. Just want to wrap up with some kind of important tidbits to take home. Again, we've talked here a bit about how cold starts do work in Lambda and how they could potentially impact you. Again, overwhelmingly for most production applications, cold starts aren't going to cause you pain. That said, there can be times where it can, and it can also be a impact to specific workloads that are very latency sensitive. We've also talked a little bit about concurrency. So in Lambda, a single execution environment can only execute upon a single request at a time. And then as subsequent requests come in, they'll cause more execution environments to be spun up. So again, depending on your application, this could mean that you could see bursts of cold started Lambda functions. To basically help solve for those two issues, we announced and launched Provisioned Concurrency towards the end of 2019. And again, with Provisioned Concurrency, this allows you to basically effectively pre-provision execution environments such that you don't have to worry about dealing with the cold start execution time. And then those environments will basically always have that warm start execution environment experience. We talk a little bit about what this means to you from a performance perspective, talk a little bit about how INIT still matters and how you still want to be really sure about the INIT performance that you have, and how you think about how memory can matter. And then finally, again, because this is for really latency sensitive applications, it may not make sense for things like async or the stream or polling based workloads. You really have to think about how much it matters for you to have those be really fast, given that, again, they're not interactive. So they're not returning a request response back up to a client. Beyond that, we think that provisioned concurrency is really going to be the best trusted way for customers to do things such as pre-warming. Again, I didn't talk about how customers have done pre-warming in this talk because typically it's been kind of hacky and not really worked that well. We really find that provisioned concurrency is going to be the best way to do that. You can read all about this and more things about serverless at aws.amazon.com/serverless. We've got all sorts of in-depth guides, use cases, customer stories, links to our documentation, links to developer tools, a whole bunch of stuff that you could find here. And then again, I want to thank you for joining us. Again, my name is Chris Munns. You can find me at munns@amazon.com or at Chris Munns on Twitter. We're going to stick around here and try to answer a few more questions. Again, thank you for joining and asking questions throughout this talk. We really appreciate it. Please provide feedback in the linked polls, and I hope to see you here in a future tech talk. Thanks again.